Let's just say we have the answer or the number 0.3333333 dot dot dot. The dot dots mean the threes go on forever. Not just a little while, they literally go on forever. They never ever stop. Threes are going on forever and ever and ever. And I know that this idea of decimals that can go on and on forever seems a little weird at first. How can something go on forever? Well, in math, we can have numbers that go on where the decimal literally goes on forever. So the way that we write this repeating decimal is we say, we represent it like this, 0.3, and we put a little bar over the 3. The bar over the 3 just means that the 3 goes on forever. It's 3, 3, 3, 3, 3, 3, 3 beyond the decimal point. So the tenths is a 3, the hundredths is a 3, the thousandths is a 3, the 10,000ths is a 3, and so on and so on. And of course, these 3's that go way, way, way far to the right, they don't have much value, but they nevertheless go on forever. Let me give you another quick example, just a couple. What if we had something like 0.62626262 dot dot dot? You see the repeating pattern. 626262. We can, of course, have things like this pop out of our answers as well. And the way we write something like this would be 0. What do you think? 62. But the bar goes over the 6 and the 2. The bar tells us what is repeating. 0.626262 forever and ever would look something like this. Let's pick one more and then we'll solve our problem. 0.3455555 dot dot dot. You see the pattern here is a little different because these first two numbers are not repeated. So this would look like this, 0.345, but the bar would only be over the 5. So when you write repeating decimals, the numbers that have no bars over them are just there, but the numbers that do have a bar over them are repeated. And you can have 1 digit repeat or 2 digits repeat. I can give you more examples with 3 and 4 digits repeating. It's just going to come up as we solve our problem. So I wanted to kind of show you what a repeating decimal was. Now you need to get used to the idea when we do long division, sometimes we get repeating answers. So let's do an example and figure out when that might happen. Let's say that we're going to take the number 1.3 and we're going to divide it by 0.3. So just like last time, we want a whole number on the outside. So we plan to move the decimal 1 spot to the right, which means we also must move that one spot to the right, which means that we're really not going to solve this problem at all. We are going to solve the related problem, which is 13 divided by 3 when we move the decimals. Now, we explained already why we are allowed to move these decimals before. It's like multiplying this one by 10, but then in order to keep it balanced, we multiply this one by 10. So even though we multiply by 10, we do it to both of them, and so we don't change anything. Now, how do we proceed? Well, we're going to solve this problem. There's an invisible decimal point after the 12, so we can put that up in our answer. The decimal will live up there. We'll extend this bar a little bit. You'll see in a minute why we need that. And let's just go ahead and solve this guy the way we think. 3 times what is 13? Well, 3 times 4 is 12. 3 times 5 is 15. That's too much. So 3 times 4 is 12. So we multiply and subtract. 13 minus 12 is 1. So we got a remainder of 1. And we do not have any extra zeros. So we don't have any extra digits to drag down. So we said in the previous lesson that you really want to try to get a remainder of 0. And if you don't have one, then go ahead and add a 0 after the decimal. And so let's go ahead and do that exact same thing that we were doing in the last lesson. Let's go ahead and add a 0 here. And so now we can drag this down after the subtraction. Now we have a 10 down here. Now what do we have? We have 3 times something is 10. Well, 3 times 3 is 9. 3 times 4 is 12. So it has to be 3 times 3, which is 9, subtract, and you get now a 1. Okay, now look at what's going on here. The first time we subtracted, we got a 1. So we said, okay, we want a remainder of 0. So we add a 0, drop it down, do the process again, and again we got a remainder of 1. It looks like the remainders are starting to repeat. So let's do the process again. Okay, well, we want to drag something else down. We want a remainder of 0. So let's go ahead and add another 0 after the decimal, which we are allowed to do. And let's drag it down. Look, we get exactly the same thing we got before, a 10. So again, 3 times 3 is 9. This is as close as we can get. 3 times 3 is 9. So we dragged a 9 there. Again, we get a 1. So you see, this process is going to continue forever. If I say, okay, well, I'm shooting for a remainder of 0, I'll just add another 0, drag it down, I'm going to have a 10. I'm going to get another 3 here. I'll do the same thing again, I'll get another 3 here. I'll do the same thing again, I'll get another 3 here. This process, we can just keep going till the end of time, because I'm shooting for a remainder of 0, and in the previous lesson, I was able to always get a remainder of 0 by doing this. But here, when I'm adding the zeros after the decimal, I can never get a remainder of 0. All that happens is I continue to get a repeating set of decimals up here. In fact, I can just go again. I'll say, okay, well, I'll add another 0 here. I'll drag it down here. Then 3 times 3 is 9. And I'll subtract again. And I'll get a 1. And then I'll have to do the same thing again. I'll continue getting 3s. So what I will then say is the answer to this problem is exactly equal to 4.33333 forever. What we say is 4.3 repeating. This is how you write your answer, 4.3 repeating. So when I said in the beginning, education's a series of lies, I kind of lied to you a little bit. In the last lesson I said, for decimal division, we want to always get a remainder of 0. And you are trying to do that. But sometimes you're going to notice that this process will never end and you'll start to see a pattern. And as soon as you see the pattern such that you'll never be able to stop doing it over and over, then you just freeze and you go ahead and write the answer down with a repeating decimal. That is how we're going to solve all of these problems. So let's take a look at problem number 2. Let's say we have 0.2 and we'll divide that by 1.5. All right, so same story, different day. We don't want this decimal here. We'll move it one space to the right in both cases. So we will actually be solving a related problem, which will be 2 divided by what? 15. Look at that. We're taking 2 and dividing by 15. But what we have here is always an invisible decimal point in every problem statement. I'll go ahead and extend this over. I know I'm going to need it. And let's see if we can figure out what to do. Now, when we look at this problem, this is a little bit different because notice that 15, it can't really go into 2. Even in the beginning, normally we say, okay, 3 can go into, it can't really go into 1, so we consider 13. How many times can 3 go into 13? 3 times 4 is 12. That's what we did. But here, the only digit we have is 2. And it's too big to go into 2, so what do? Well, you have to go ahead and stick a 0 after the decimal because you're allowed to put as many zeros after a decimal point as you need. And we need another digit to continue with the division process. So the answer will have a decimal point there. And now we consider how many times will 15 go into 20? How many times will 15 go into 20? Well, it can only go one time. So we put a 1 right here. 1 times 15 is 15. We could borrow and all that, but you know that 20 minus 15 is just 5. So we get a 5, which of course means the remainder is not 0. We don't have any more digits to drag down, but we can't stop. We need to either have a remainder of 0 or we start to see it repeating. So let's put a 0 there and let's drag 0 down there. How many times can 15 go into 50? Or 15 times what is 50? Let's just check 15 times 3. 5 times 3 is 15. 1 times 3 is 3, plus 1 is 4. 45 is as close as I can get. So the answer is 15 times 3 goes here. 45, that's as close as I can get. Again, I subtract. 50 minus 45, you could borrow if you want, but I think you all know that the difference there is 5. So you start to see the same thing happening. We got a remainder of 5. We dragged a 0 down. We did the process again. Again, we got the same remainder of 5. If you want to be extra sure, then we can just add another 0 there, bring it down. We get exactly the same thing as before. And you can see that, again, it's going to have to be 15 times 3 is 45. Again, the remainder is 5. So I can keep doing this process of adding zeros and trying again, but I will never get the remainder to be 0. It will just repeat in this fashion. So here, the answer is going to be, there's really nothing here, so it's like an invisible 0. The answer is 0.13 with a repeating bar over the 3. 0.113 where the 3's are repeated forever and ever and ever. And you need to kind of get used to that. If you grab a calculator and just start dividing random numbers, a lot of times you'll start to see repeating decimals that go on and on forever. All right, let's take a look at the next problem. This process gets much, much, much easier as we practice more and more problems. So let's say we have, for our next problem, 0.2, and we want to divide that by 0.03. 0.03. Now in this case, I want to move the decimal 2 spots to the right. So I have to move this 2 spots to the right. There's 1 spot, but I want to move 1 more spot to the right. So that means I need to kind of insert another 0 there. You can kind of put the 0 in there if you want to, because you can add zeros after a decimal as much as you want. And so what you want to do is then solve the related problem. Once I move it over here, it'll be 20 divided by 3. 20 divided by 3. Make sure you understand. Decimal moves twice, decimal moves twice. So I have 20 divided by 3. This is the problem that I actually want to end up solving. Again, don't forget, after every whole number is an invisible decimal. So there's an invisible decimal here, and I kind of wish I had given myself a little more room. Sorry about that, because I don't want to collide there, but I guess I should have given myself a little more room. So 3 times what is 20? Well, 3 times 6 is 18, and 3 times 7 is 21. So it has to be 3 times 6. That's going to be 18. 20 minus 18 is going to be 2. You can borrow if you want, but I think when you count it from 18, 19, 20, you see the difference is 2. Now I got a remainder of 2, and I don't have any more digits here, but I can't stop there. I want the remainder to be 0. So what I'll do is I'll just add a 0 here, which doesn't change anything, and I have now a remainder of 20. Now, 3 times what is 20? Well, 3 times 6 is 18. That's, again, as close as I can get. So I subtract, again, I get 2. I'm starting to see a pattern repeat because I got a remainder of 2 here. I also now got a remainder of 2 here. So I'll just do the process one more time to confirm. Again, I got that 20 down there. 3 times 6 is 18. That's as close as I can get. And the same process is going to happen, 2. Every time I do it, I'm going to get a remainder of 2, remainder of 2, remainder of 2. I can keep dropping zeros until I'm literally exhausted, but it's not going to change the fact the answer to this problem is 6.6 with a repeating bar. Because the 6's here repeat forever and ever and ever. 6.6666666 means 6.6 repeating with a repeating bar. All right. Hopefully by now, I think you kind of understand what to do. It's a little, maybe not perfectly in your mind, but you understand sort of what to do. As we work the next few problems, hopefully it will become a little more burned into your mind. What about the number 1.1, and we want to divide that by 0.3? So what do? We have to move the decimal 1 position to the right. So we move this 1 position to the right. So we want to solve the related problem, which is 11, after I move the decimal, divided by 3. And don't forget that every whole number like this 11 has an invisible decimal, which means the answer will have an invisible decimal point right there. Now 3 times 3 is 9, and 3 times 4 is 12. That's too far. So 3 times 3 is 9. Now 11 minus 9, you can just count up from 9, going up from 9, 10, 11. So the difference there is 2. And so I have a remainder of 2. I can't stop there. I want the remainder to be 0, or I want to see a repeating pattern. I don't have any more digits here, so I add a 0 after the decimal, and I drag down. Now I have a 20. 3 times 6 is 18. 3 times 7 is 21. That's too much. So it has to be 3 times 6, 18. Subtract, again, I get a 2. I'm starting to see repeating. But just to make sure, I want to then drop another 0 down. So now I have that 20. 3 times 6 is as close as I can get, which is 18. And subtract, I get a 2 again. So if I keep adding zeros, I'm going to keep getting 20 and 20 and 20 everywhere. So I can see that the pattern is going to then repeat. So the answer to this problem is 3.6 with a repeating bar over the 6. 3.6 repeating. That's the way you say that out loud. All right. Now we're cooking, doing, I think, a good job. Let's take a look at the next problem. Let's take a look at 0.14, and I'm going to divide that by 0.09. So on the outside, I want a whole number. I move the decimal 2 spots, so I have to move this decimal 2 spots. So I'm really going to solve the related problem, which will be 14 divided by 9. After I move the decimal in both spots, 14 divided by 9. And just like always, every whole number has a decimal point after it, and that means that's where the decimal point will go in the answer. 9 times 1 is 9, and 9 times 2 is 18. So it has to be going only one time. 9 times 1 is 9. Now what's 14 minus 9? We can just start at 9 and count up. 10, 11, 12, 13, 14. That's a difference of 5. So I have a 5 right here. That's my kind of my remainder, but I want a remainder of 0. I don't have any more digits here, so I can just add a 0 after the decimal and drag it down. Now I have a 50 right there. Now 9 times 5 is 45. That's as close as I'm going to get. 9 times 5, multiply, get 45. And subtract 50 minus 45 is going to be 5, and you start to see repeating. I have a 5 for a remainder here and a 5 for a remainder here. But again, I want to drag down the next digit to try to see what happens, see if I can get it to work out. And so I drag, and again, I have a 50, which is the same thing I had before. So what's going to happen is 9 times 5 is 45. That's going to be as close as I can get, and I'm going to get another 5 here. So if I keep adding zeros and keep dropping them down, I'm going to keep getting 5s over and over again. That's the bottom line. So the answer to this problem is actually equal to 1.5 repeating, with a repeating bar over the 5. With a repeating bar over the 5. That was the halfway mark. Halfway mark. Let's take a look at the problem. 3.8, and we'll divide that by 0.6. So on the outside, we have one decimal to move. So we move one decimal this way. So what we're going to do is, instead of solving this, we'll solve the related problem of 38 divided by 6. This is what we want to solve. Now, just as always, every whole number has an invisible decimal there, so that's going to be in the final answer. And then you have to ask yourself, 6 times what is 38? I don't know. Well, let's try 6 times 6 times 8. That's 48. That's too much. 6 times 5. That's 30. 6 times 6 is 36. That's the closest as I can get. So 6 times 6 is 36, and I subtract. 8 minus 6 is 2, so I have a remainder of 2. Now I can't stop because I want a remainder of 0. So I grab the next digit. I don't really see one, so I add a 0 there, and now I have this 20 down here. Now, 6 times 3 is 18. 6 times 4 is 24. So it has to be 6 times 3 is 18. Subtract. 20 minus 18, again, is 2. I'm starting to see a pattern here because I'm starting to get the same remainder. But let's do it again. Put another 0. Again, I get a 20. Same exact thing is happening. 6 times what is 20? It's 6 times 3 is 18. And I can subtract again and get another 2. I'll keep doing this again and again, adding zeros. I'll keep getting the same exact thing. So really, the answer to this problem is 6.3 repeating. 6.3 repeating. Over and over again. 3, 3, 3, 3, 3, 3, 3, 3, 3 to the end of time. That's what it'll be. Now this one, I want you to pay extra attention to because it's a little bit longer. It's not hard, but we just have to be a little careful. Let's take a look at the problem. 0.05, and we'll divide that by 0.11. 0.11. So the first thing is, I want to move the outside decimal 2 spots, so I also have to move the inside decimal 2 spots. So we will then solve the related problem, which will be a 5 under the division house, divide by 11. 5 divided by 11. Now, we know that every whole number has a decimal after, so we'll just put it up there. And then we ask ourselves, 11, can it go into 5 or not? It can't. So you're kind of stuck immediately, but if that ever happens, then just add your first 0 right away. 5.0 is the same exact problem. Now, how many times can 11 go into 50? Well, 11 times 4 is 44. 11 times 5 is 55. So it has to be 11 times 4, which is 44. Now you can do the borrowing and all that, or you could just subtract or go up from 44 to 50. Let's count up. 45, 46, 47, 48, 49, 50. There's a difference of 6 here. So we subtract and we get 6. Now we always want a remainder of 0. So we try to grab the next digit. We don't see one. So we just add the 0. And now we have this 60 down here. All right, we have the 60 down there. Now, 11 times 5 is 55. 11 times 6 is 66. So we can't be 6. It has to be 11 times 5, which is 55. And we're looking for a pattern. So far, I don't see a pattern, but I know that 60 minus 55, again, is 5. All right, so I'm still not, here I had a remainder of 6. Here I have a remainder of 5. I don't see a pattern yet. So, but I also don't have a remainder of 0. So add another 0 here, and now I have a 50 down here. 11 times 4, that's going to be 44. That's as close as I can get. I subtract. Now, I'm starting to kind of see a pattern. Here I had 50 minus 44. That gave me a 6. 50 minus 44 again gives me a 6. The pattern is not totally clear to me, so I add another 0, and I keep dragging this down. Now I have a 60. I'm starting to kind of see a pattern. 11 times 5 is 55. That's as close as I can get. 11 times 5 is 55, and I subtract, and I get a 5. Now I can actually see the pattern. Because what happened is I had a 60, and then a 50, and then a 60, and if I do this again, I'm going to get a 50. So you can see what's happening. 4, 5, 4, 5. It'll be 4, 5, 4, 5, 4, 5 forever and ever and ever. That's what's going to be the answer. So this problem is 0 point, because there's nothing here. This is 0. 4, 5 bar over both the 4 and the 5. So it's 0.45454545. Grab a calculator and take this divided by this, or 5 divided by 11, and you'll see that this is what you get. Now we do have a couple more problems, but I want to kind of point out to you that look what's happening here. When I take 5 divided by 11, where I have a smaller number on the inside than I have on the outside, it cannot go even one time. That makes sense, because remember, division is seeing how many times can this fit into here. But 11's bigger than 5. So it can't even fit one time. This is less than 1, right? Same thing happened, where was it at? Over here. I had, if I'm trying to take 2 and divide by 15, 15 cannot fit into 2 even once. That's why the answer comes out to be less than 1, 0.133, and so on. That's what's going on there. All right, we have another problem to work. I think I can steal some board space over here and handle it. Let's take a look at the following problem. 0.84, and we'll divide that by 0.09. And we want to, of course, have no decimals on the outside, so we move it 2 times, move this one also 2 times. So what we'll do is we'll solve the related problem. We'll have 84 underneath, and we'll divide that by 9 on the outside. But just as always, there's always an invisible decimal point after a whole number, which means there's a decimal in my answer. So 9 cannot go into 8, but 9 can go into 84. 9 times 9 is 81. That's as close as I can get, because 9 times 10 is 90. So 9 times 9 goes right here, 81. 4 minus 1 is 3. Of course, I want a remainder of 0, so I grab the next digit. I don't see 1, so I just add the 0 here, and now I have this 30 down here. 9 times 3 is 27, and 9 times 4 is 36. So that's too much, so it has to be 9 times 3. That's 27, and subtract. Just counting up from 27, 28, 29, 30, I can do the borrowing if I want, but the difference here is 3. So again, I want a remainder of 0, and so I grab the next digit. I don't see 1, so I just add this 0, and now again I have 30. And now I start to see the pattern. 30s are appearing. 9 times 3 is 27, and 9 times 3 is 27, subtract, and I'll get 3. And so this process will again repeat over and over and over again. So the answer to the original problem is 9.3 with a repeating bar over the 3. 9.3 with a repeating bar over the 3. And that is the last problem in this lesson. The first thing we did was start out by talking about the idea that a decimal, you can have an infinite number of digits after the decimal point, and those can have patterns. They don't always have patterns, but they can often have patterns. Repeating decimals, that's what it's called. And we talked about the bar and how the bar works and so on, and we talked about what to do. When you're dividing decimals, basically you're looking for 2 things. You keep doing the process until the remainder is 0, or if you keep getting the remainder over and over again, even when you're adding these zeros, then you've uncovered a pattern in the answer. Then you can just stop, because you can't do this till the end of the universe. You have to stop somewhere, and then write the answer down with the repeating bar. I actually encourage you to grab a calculator. Just grab a calculator or a computer and divide these numbers on a computer, and you will see the repeating decimals in all of these problems. So I'd like you to solve all of these yourself. When you feel like you're getting the answers, follow me on to part 2. We'll wrap up the idea, get more practice with decimal division with a repeating decimal. Learn anything at mathandscience.com.